Good afternoon and welcome to the CERIAS Security Seminar from Purdue University. Today we have a special event. Every year in March or April we have the CERIAS Annual Research Symposium. I think we have our theme music going. And in that event we host a poster session, and this year I think we had 46 different posters representing some of the research projects here on campus. And we have a contest whereby our partner organizations select 3 that they find the most mature or most interesting or most applicable or just most advanced. They have different criteria for selecting 3 as the top posters. And so today we have the privilege of hearing from 2 of those groups, 2 of the top 3 of these 46 posters presented this year. And so our first poster is from a team from the Aeronautical Engineering Department led by Professor Dan Delaurentis, and 2 of his students, Zhemei Fang and first name? Payuna Uday, are here to talk about their poster, Increasing Robustness and Resilience, Assessing Disruptions and Dependencies and Analysis of Systems Alternatives. And that systems of systems is the key word there. A lot of his work involved in that area. Please.
Hi, good afternoon, and thank you for this opportunity to be here and share our research with you today. As you can see from the authors, this is truly a team effort. We've got quite a few people on it, with 2 professors, a senior research associate, and 3 PhD students. And before I start, I'd like to acknowledge my friend Cesare. He presented this poster, and I'm sure it was his effort that got us the prize. So let me just zoom out quickly first. So essentially what we've been trying to do over the past 4 years, which is look at systems of systems and try to analyze and synthesize the interdependencies between systems in large-scale complex networks. This project has been funded by the Department of Defense. So when we started out, it was quite more of exploratory research. We were trying to see how we can analyze and model interdependencies. And over the past few years, this research has really begun to take shape with the final goal of having something called an analytic workbench with a suite of tools that an SOS engineer can go to answer specific questions. So what exactly is a workbench? I'll begin, and I guess this would probably be like the main takeaway from this presentation, which is the overview part, as you can see here. So what we're trying to get at is we have the real world, and there are a lot of complex networks and systems and things that we're interested in. Systems engineers at...
Could you zoom in one more time?
One more time? Okay, here we go. And so SOS engineers typically are interested in analyzing and solving problems in the real world. Now, what you see in the blue box is our analytic workbench, which hosts a suite of tools. So what the SOS engineer can do is come to the workbench with his or her questions, come with the specific data sets that they have or don't have, and identify the key aspects that they need to analyze in the real world problem, identify the most appropriate tool or the most appropriate sets of tools that can be used to answer those questions, and then work in an iterative fashion with some kind of truth model or simulation to go back and forth and see, has my analysis been right? Is this the answer I want? Is this giving me a set of solutions that are going to be useful, etc.? So this is essentially the main focus of our research. Now I'm going to just spend a couple of minutes talking about 2 of the methods, and then I'll hand it over to my colleague Zhemei, who will talk about the rest of the poster. So the first is the systems operational dependency analysis, which is the bedrock of Cesare's research. So what the intent of his work is to model a system of systems as a directed network where the nodes represent either the component systems or the capabilities. So the links within a particular network represent the various kinds of dependencies between systems. And the focus of his work really is to build such a network and see what happens when there are partial disruptions or complete disruptions on certain nodes, and what are the downstream effects on the overall capability at the SOS level. So this is more of a very generic approach which can be applied at many levels, and over the past few years he's actually managed to apply it in terms of cybersecurity and look at what happens when there are disruptions, how can we deal with them. And the approach is not just about avoiding disruptions, which would probably be impractical, but more of how can we be robust to, if a disruption happens, how can we be robust to it, and how can we recover and minimize the performance loss on some level. And the next piece of work is the system importance measures, which is the central focus of my research. So what this does is essentially look at presenting a set of measures called system importance measures that tries to rank the systems in a system of systems as to how important are they with respect to overall performance in terms of a disruption. So for example, as you can see in this little table, we can have a certain set of systems in our SOS. We can analyze what happens when each of them are disrupted and what are the impacts on the highest level, and we can rank them as having a high disruptive impact, a medium or low. And essentially what this gives us is a visual representation of which areas in your SOS need attention the most and which ones are perhaps those where you can actually downgrade certain features and optimize your resources to channel them towards the more highly disruptive systems. So the way this essentially works is we would use some kind of representation of our SOS. We'd have to identify disruptions and look at what kinds of recovery or mitigation options we already have, perform a system importance analysis where we come up with a ranking of the different systems, and then we would use design principles that are specific to SOSs to make improvements and see where can we improve our resilience or our robustness and how can we do it. So essentially, I think Cesare's work and my work on some level go hand in hand, which is one of the, we think, neat features of our workbench, which is you could use one method to model your system of systems and look at various features or emergent behavior, and then you can use my method to quantify the outcomes of that modeling process and come up with some kind of visual representation that can aid decision making and be able to translate the technical content to more management level decision making choices. So now I hand it over to Zhemei for the next two methods.
Thank you. So I will talk about the methods of my colleague Navin and my work. So I will start with So this part is about the robust portfolio optimization. So the main goal is basically to choose like a bunch of systems, like which kind of systems to form the architecture that can be more robust to certain kind of uncertainties or some disruptions. So here he borrowed the idea from the financial engineering about the portfolio and also the conditional value at risks. So here first he applied a bunch of connectivity rules, like for example like the compatibility, and they have some constraints of they have some requirements constraints. So there are a bunch of rules here. So this one kind of set up how the systems can be connected to form the architecture. So the objective is to maximize the performance index. So with this connectivity constraints. So the result he got here is like more like a trade-off space that amount between performance and the risks. So the decision makers, they can choose what kind of architecture, what kind of combination of systems that's more robust to those kind of uncertainties. So this is basically what it's doing. So my method is kind of similar to what Davin's work. So but more like
I think we just lost the. Yeah, let's go back.
Sorry. So you can see here is the analytic workbench is like more like consistent, try to capture different perspectives of the architecture. So mine is like based on the selection of different systems into the architecture. We take into the consideration of stakeholders how they look at those different combinations of systems, how they coordinate with each other. So this part is not complete fit into cybersecurity part, but it's kind of try to more comprehensive. This is kind of in progress work. So our analytic workbench. So we are also like trying to like have some connection with the industry. So now so far we have connected with the Army and also the Navy Dalgary and some work with the MITRE. So we actually for MITRE we have they applied the solder and SDNA to look at what the effect of these disruptions and what is the effect of the disruption of development. So this is what we have. You have questions?
Yeah, any questions for either of them?
Does
Your competitors on the slides.
does your analysis at all help you forecast where there might be higher chances of disruption in systems?
Some of these tools,
Can you see
okay. Some of them, they would tell you which ones are more critical at present, or you could even include, like for example, in the system importance measures, I have a certain set of expected importance measures based on your forecast of, what is the likelihood of being disrupted, what is the likelihood of your recovery measure being available. So to some extent, yes. So you can plug in some stochasticity to get at what is the expected criticality of your systems, and that's where we are right now. Not sure if I answered your question. Do you mean in? Okay.
Hi, I have a question regarding the disruption you're mentioning. Are you talking about actual attacks against the system? Are you also including things like natural effects, like mountains disrupting radio wave, transmission, or are you just talking about actual attacks?
So the way we are right now is we're considering disruptions, but we're not so much considering the causes of the disruption. So we're looking at disruptive impacts.
Okay.
So that's how we're
Thank you.
allowing for those.
So in this process, do you baseline potential risks of disruption at all, or just assume there's no disruptions and then go from there?
I'm sorry, could you repeat your question?
So when you look at your modeling, there might be, I don't know if there's such a thing as noise risks in the background, noise disruptions versus deliberate or accidental. Is that something that you consider at all?
I'm not sure about some of the other methods, but from what I know of the two I spoke about, what we do is we first build a baseline, fully working system of systems, and then we try to see what impacts like partial disruptions can have or complete disruptions can have. So we don't have, so we do build a baseline first to calibrate for with or without disruptions.
All right, thank you.
Thank you.
Thank you very much. I should have told you that you're presenting to your competitors in the poster contest here, but I think their questions were kind. One of our other posters, and I believe, did you receive the first place selection? Okay, this is a poster by Rohit Ranchal, PhD student with Professor Bhargava in the Computer Science Department. And do you want to pull your slides up? And I'll let you just introduce the policy-based distributed data dissemination.
Hi, thanks CERIAS for this opportunity to share the work. And I think I forgot to mention, put it on the slide, but this work was funded by NGC, and they have been supporting us for last few years, and with their support, and they are part of they're CERIAS partners, and that's how we got introduced to them. And I think with their support and with CERIAS support, we've been able to do this research. So let me start. I work with Professor Bhargava in computer science, and so this is a brief outline of my talk. Let me start with some motivation. So the main idea behind composite web services is that independent services are composed together to accomplish a task. In case of services, basically handling client requests. So when a request goes to a composite web service, there are multiple interactions which take place in the background that may share user data. And let me give you an example of a composite web service. So for example, here we have a shopping service, which is a composite service composed of seller, shipping, and payment as component services. So here a user is sending an order request to a shopping service along with some of its data. And this data is being shared with other component services by the shopping service. And the main concern here is that there is no visibility into how this data is being shared with the component services, and if these services are authorized to receive users' data or not. So basically, data sharing is happening across unknown endpoints, and there may be data sharing violations, privacy violations from a user's perspective, and these may go undetected. Now, one way to control access to the data is by specifying the policies. And the current composite web service infrastructures lack a policy framework through which users can specify policies, communicate them to other services, and ensure their evaluation and enforcement. Now we have existing security mechanisms, for example, HTTPS, which are really message-based mechanisms. So they provide a secure channel between 2 points, and they don't provide any mechanism or guarantees to evaluate and enforce policies. Okay, so the main objectives of this research are to ensure the evaluation and enforcement of user-specified policies for data dissemination, and ensure that each authorized service is only able to receive the data for which it is authorized, and prevent any unauthorized service from getting any data. So let me give a little bit of formal description of the underlying problem. So here we have a user which has a set of data items, and it would like to share this data with a set of hosts. Now each host is only authorized for a subset of data, in this case different data items. But the user can only interact directly with host 1. Similarly, host 1 can only directly interact with host 2 and host 4. So each party has to share all the data in order to ensure that each party gets access to the data for which it is authorized. But if all the data is being shared by every party, that is against the goal of the system, because each party is only authorized to receive certain subset of the data. So we propose a solution to address this problem. So basically, the way the solution works is that the user specifies the items as key value pairs. So key is the public part and value is the sensitive part. So key can be, for example, email, and the value is the actual email address, which needs to be protected. And then the user specifies the policies for each data item to control access to them. And these data items are encrypted. And the user also defines a function and shares these things with each party. Now each party using the function can evaluate the function and get access to the data for which it is authorized. And it would only get access to the item if it is authorized. If it is not authorized, basically the data would not be disseminated. Now, in terms of real-world implementation of this solution, we achieve this using active bundles. So what is an active bundle? So basically, it's a self-protecting data encapsulation mechanism which provides secure data dissemination. So it has 3 parts: sensitive data, which is encrypted, which we need to protect, and metadata are the access control policies which control access to this data. And thirdly, we have virtual machine, which is really the code which controls access to the data. Basically, it evaluates the policies, enforces them, and ensures data dissemination, and also protects the whole bundle. So these are the main components of the active bundle. So in order to ensure correct dissemination, it follows certain steps. The first step is the authentication of the host. So whenever this active bundle is shared with a host, it needs to authenticate the host. And this authentication can be based on standard authentication mechanisms like password, certificates, PKI. And after the host is authenticated, the host would send a request for a particular data item, at which point it needs to be authorized for this particular request. And the authorization, again, can be based on different access control models, for example, role-based or attribute-based. And the policies for these access control models can be defined using standard languages like XAML. Now, since the data inside the bundle is encrypted, we need to manage the keys for decryption. And there are a couple of ways to manage the keys. So one way is to include the decryption keys inside the bundle itself, but which is prone to attack. So for example, a host which receives the bundle can attack the bundle and get access to the keys. Another approach is to use a third-party service for key management, which can store the keys and distribute the keys to the authorized hosts. And so the approach which we use is dynamic key derivation. And this is achieved by using the information generated during the execution of the active bundle. And so if this execution is correct, only then this information is generated and the keys can be driven. Otherwise, the keys are not generated correctly. But still, this is prone to modifying attacks. So an attacker can tamper with the policies of the active bundle and change the execution of the active bundle. So the active bundle needs to be protected, needs protection against tamper attacks. And the way which we achieve this is using integrity verification of the active bundle steps. So what we do is that for each step, we calculate the integrity of the step and the resources which it uses, and uses the digest from this integrity calculation to derive the keys. Now, if there is a modification attack to the active bundle, the step is modified, and therefore the digest of that step will also be modified. And the key which is generated based on that information will be incorrect, and that data would not be able to be disseminated. So this is the same interaction using active bundle. So in this case, instead of sharing the actual data, the user shares the data by means of active bundle along with its request. And each party is only able to access the information for which it is authorized. And the other information is still there inside the active bundle, but it is encrypted. In terms of implementation, so the way we implemented active bundle is in the form of an executable jar file, which is included inside the REST message, which is exchanged between different services. We used XAML for policies and an open source policy evaluation engine, WSO2 Balana. For experimentation, we implemented the services in Node.js. In terms of attack resilience, there are 2 aspects of it. So from a service point of view, when a service receives active bundle, how can it trust the active bundle and its execution? If there is a malicious active bundle, really what the service is receiving is a bunch of code which can maliciously compromise that service. So one way to protect against this is through digital signatures, which can be used to verify the authenticity and integrity of the active bundle which a service receives. Further, a service can isolate the execution of the active bundle using containers or VMs. Now, from a user's point of view, the user would like to protect active bundle against malicious receivers. And again, this is achieved through temper resistant by using the integrity of the code itself to derive the keys for the dissemination. Now, there are certain high security environments, for example, defense scenarios, where the active bundle can be actually executed inside a VM at a cloud, right? So this is like a third party use of third party for code execution, but the third party doesn't get access to any data. It doesn't broker any data. So this is a little bit about the cost-benefit analysis of the solution. So in terms of benefits, using this approach, we are really able to provide policy-based access control in any domain, in a known domain, a trusted domain, an unknown domain, or an untrusted domain. And basically, since it minimizes the disclosure of data, it's able to preserve privacy of the user. Further, it can do context-based control data dissemination, which is really when, if there is a change in a context, for example, emergency, under attack, or a disaster scenario, the policies can be made flexible. They can be more rigid or can be made more easy to accommodate the context and disseminate the data according to the context. And this solution is independent of trusted third parties. It does not rely on source availability. So once the active bundle is shared, anybody can get access to the data, and the source doesn't need to be available all the time. It reduces the host liability for extra data. Now this is important. Recently we have seen data breaches from Target and Anthem, and where these services were liable for the data which was leaked during the attacks. They had a lot of lawsuits and those kind of things. So the services didn't really need all the data in this case. For example, credit card information of users were leaked. So with this approach, we minimize the disclosure of the data, and that reduces the liability of a host for protecting that extra data. Now, in terms of costs, definitely there are certain overheads. So active bundle adds an overhead to the size. And of course, there's more network overhead due to that size. Now, every service has to interact with the active bundle to get access to the data. And now this interaction adds an overhead and increases the delay for the service response time. In case of services, they have to commit more resources to the execution of the active bundle. So there is a resource overhead. And in case the services use additional resources such as containers or VMs to execute the active bundle, there is possible overheads for that as well. And from the user's point of view, if the user uses a third-party code execution environment, that is an additional overhead to manage those execution environments. So we conducted few experiments to measure these overheads. So this first experiment is to measure the size of the active bundle with the increase in the number of policies. So on the x-axis, you see the increase in policies. There is an exponential increase in policies, so that's why there's a log graph as well. And on the y-axis, you see the size of the active bundle in kilobytes. And there are really 4 different versions of active bundle which we tested with. So we have 2 versions for 2 different types of policies. One is with XACML and one is without XACML. And then there are 2 different versions of active bundle with temper resistant and without temper resistance. And if you see the log graph, there is a linear growth in the active bundle size with increase in policies. And I think the main reason is because of the policy overhead. So each policy adds an overhead to the size. And this second experiment is regarding the interaction time between the active bundle versus the increase in the policies. So again, we can see that there is a linear growth in case of the XACML-based policies. So the XACML-based policies are represented by the curves in yellow and orange. And the ones without XACML are represented by blue and green. And in case if we don't use XACML, there is a constant growth, which is good. So XACML, and the main reason is this, that XACML is an old standard which was really developed for SOAP-based services. It's specified in XML, so there's a huge XML tree which you need to parse to evaluate the policies. But there are more simpler ways to define policies, lightweight mechanisms like JSON and lightweight policy engines to evaluate these policies. The third experiment is to measure the temper resistance overhead. And again, we compare this with ZACML and without ZACML. So if you see the first graph with ZACML, the overhead of temper resistance, there is a linear growth in the overhead. And without ZACML, the overhead stays constant, even with the increase in policies. And again, this has to do with the policies, ZACML policies, which are in XML. So this is still work in progress, and we are conducting further research to improve this approach. So we are testing other lightweight policy engines to improve the performance, and we also want to measure the scalability of the solution. So this was an isolated the experiments which we did were isolated in terms that there were only single requests going, right? So in a real world environment, a service is dealing with many concurrent requests. And to test the scalability of the system when there are thousands of active bundles executing concurrently, how scalable is the system? So, and of course, we want to do security testing to test the resiliency of the approach against different attacks. Also, we are exploring whether we should exchange certain state information with a third party to add more capabilities to the solution, for example, context-based dissemination and more information about the environment in which the active bundle is executing, so that it can make more intelligent decisions for dissemination. And of course, this research is applicable in several different scenarios: healthcare, defense, vehicular communication, wherever data sharing is involved. So we are exploring the application of our work in different scenarios. And that's all I have. Thanks for paying attention. I'll take any questions.
Questions? Okay, thank you. The third project that was a poster winner was also funded by the Northrop Grumman Corporation. That was a project by Professor Elisa Bertino and her students, along with a postdoc, Lorenzo Bossi. The students were Syed Hussein and Asma Salam. Their project was entitled Monitoring DBMS Activity for Detecting Data Exfiltration by Insiders. So that was our third group. Let's give a round of applause again to all of our poster winners. Thank you.